Hey folks, in 6.3 we're going to start out with rolling motion, and so I drew this diagram and I planned the video, and then when I started to think about how I was going to present it to you, I regretted something. I regretted drawing this line that goes vertically down from the center of this circle to A, and I'll try and ignore it as best I can. What I have drawn is a wheel that is rolling along the ground, and we're going to assume that this wheel is moving and it's not slipping while it's moving. So every time the wheel turns, it turns and a new part of the wheel touches the ground, and that part is gripping the ground. And so it's not going to slip, and we're not going to introduce kinetic friction. And what I want you to focus on is what happens to point B as this wheel rolls from here to here. So if we imagine the wheel rolling this way, with an angular velocity. Point B is going to rotate around the center of the wheel like this. So this red line that I'm drawing represents the linear distance that point B is going to travel from its position when the wheel is here to its position when the wheel has moved a certain distance. So those two distances are related, because if the wheel doesn't slip, then every particle of wheel along this arc will get its own turn in contact with the road. What that means is that this straight line distance is equal to this arc distance. So I've drawn delta x here. That should say delta x of the center of mass. So the center of mass displacement of this wheel goes from this point to this point. The linear distance covered by point B for that same rolling motion is this arc right there. And because this wheel is not slipping, those two are equal. Now, this is an arc, and so we use the letter S for arc length. We're not going to use it really beyond this video, but here it is. So as long as there's no slipping, so if there's no slipping, if the wheel grips the road the entire time, then the center of mass distance that the wheel travels is equal to the length of this arc along the surface of the wheel. Now, I happen to choose not a full rotation on purpose, so there'd be some arc that wasn't part of this. But if this wheel turns this much, so to get point B all the way around so that it's now at the bottom, that's a certain arc, and the wheel will also displace its center of mass by a certain distance. So that's like a pretty key relationship there. Now, let's stick with this for a minute. While point B is moving a linear distance along that arc, this R line here, all right, so that radius of the wheel, that line is sweeping an angle, theta. What do I mean by sweeping? I mean, okay, it starts up here, and as if it's sweeping the ground, it sweeps all the way until it's vertical. And so sweeping that angle, theta, is just an angular displacement. And we've studied circles before, and so when we have an angular displacement of a point a certain distance away from the axis of rotation, the product of those two values is also going to be equal to that linear distance. So I can say, and that arc length right here along the circle is equal to r theta, whatever that distance is, times that angular displacement. So if I put those together, I get the following relationship. So delta x of the center of mass is equal to the radius of that wheel times the angular displacement of the wheel while it was getting displaced. Now, you're going to look at that, and maybe if you look back in your notes, you'll be like, I already have this equation. It's delta x equals r delta theta, and the only thing that was missing was that center of mass. And so that's a really important distinction, that regardless of whether you have something that's purely rotating, like a pulley, or something that's rotating and translating, like a wheel rolling, the same equation governs their motion. So delta x for like a pulley would just be like the linear distance that the outside of the pulley moves, whereas this is the actual linear displacement of the wheel itself. That's really neat because if we wanted to, say, figure out how far a car has gone, we would need to know the radius of the tires and how many times the tires had rotated. Now that's data that's not readily available on a car, but if I continue on this logic, I get an equation that's very useful to a car. This equation can be replicated for velocity, and I could write a similar equation that said the velocity of the center of mass is equal to the radius of the wheel times the angular velocity of the tire. Now, angular velocity can be measured in RPMs, and so you can actually know how fast your car is going based on the radius of your tire and the angular velocity of your wheel. And this is actually how your odometer works. Your speedometer works. The velocity or the speed of your car as reported by the speedometer is just based on the radius of the tires that you have on the car and the rotations per minute of your car's engine. So these equations together can be used to describe rolling motion. We tend to focus on this one because it's velocity, and that's a more important kinematics concept, but this equation is actually in your equation sheet. Summarize all this. Rolling without slipping means that a wheel's center of mass and a point on the outside of the wheel travel the same distance in the same time. So that's what this equation means. And then we can also translate that to the velocity of a wheel's center of mass is equal to the velocity of a point on the outside of that wheel. The last bit of this is if a wheel rolls and slips, this relationship is no longer true, and also energy is being removed because if the wheel slips, slipping motion induces kinetic friction, and so there's going to be some heat created and dissipated. There's no longer energy available to move the object. So we don't really cover rolling with slipping as much as we cover a couple examples of rolling without slipping. And that's it.